remember to turn off the light?
Yeah.
Which means it's nap time. Okay. Tom's gonna take over. Everybody see?
Out here so I can see it.
Well, first, I'd like to thank my brother David, or Dave as he's known here, for getting me into this club. Also to thank him for getting me into ham radio back in the late 60s.
Really?
Bless his heart. And I hope his health improves so he can start participating again soon.
You might need to speak up, Tom.
Okay. Yeah, I got my hearing aid turned up a little bit, so I'll turn it down.
Turn it down, then
and I'll
again.
speak up. By the way, if you do ask a question, you better speak up too, because using the hearing aid is pretty bad. Now, first of all, we're going to talk about radio before 1900. So, and I'm not even going to end up with Tesla, Marconi. I'm certainly not going to get to Armstrong. So, to take the phrase from a popular story, I'm going to talk about the deep magic. Magic before the magic. So we're going to step back from the technical things, one step, maybe 10 steps, and ask the question, what might have been the first radio? Okay, everybody got a picture of that in their head? The first, what they think the first radio. Well, here's my picture. Now, what you have here off the screen is a very wideband DC to X-ray energy source shining down on this fellow through a very narrow bandwidth filter. It's the atmosphere. Gives him a nice strong signal in the half micron band. And he's built this AM modulator,
It hurts already.
which with my half micron band receiver, I can pick up his signals. And it works pretty good over a few miles, right, a couple of miles. The problem is, the bandwidth's pretty low, and there's only a few signals you can send. Okay, but you might think that's kind of silly, but development is still going on in this technology. At no place less than the Vatican. So they've gone from AM modulation to frequency modulation. And the black is a no and the white is a yes. And that's the limit of the information you can send. Okay.
It's digital.
But it is a bit silly, but the main point of this is even thousands of years ago, the need for long-range communication was seen. If you could communicate faster and over longer distances, you could probably beat the other fellow that was trying to come to steal your food or whatever. Okay. So, the need was there, but real radio developed very recently. And the main reason is science developed very recently. I came across this book, titled Why Science by James Truffle. I picked this up for $1 used on Amazon.com, $4 of shipping. You can have this for $5. And I think it has a very important message for our day and time, and pass that around. But I'm just going to read a quote from Mr. Truffle. For most of the time our species has been on a planet, this planet. We live in what Carl Sagan calls a demon-haunted world. A world with mysterious, unpredictable, and often malevolent forces dominated human understanding. So what's he talking about? Well, before say, I don't know, we could take 1700, people saw lightning, they were more likely to think it was due to the wrath of God. If somebody got zapped, then some charges building up in the cloud and finally letting go. And he tells a nice little story about the medieval discussion among a group of scholars. And the discussion is how many teeth in the mouth of a horse. Well, the first scholar gets up and quotes St. Augustine, who had written on this matter. The next scholar got up and quoted Aristotle. And they were debating, and there was different numbers being tossed about. And a young man in the back of the room stood up and he said, "There's a horse outside, let's go see." Whereupon the older scholars beat him and threw him out and cast him out of the educated system. Okay, now, when the tide began to turn, when you have fellows like a fellow named Tartaglia in the 1400s, who was kind of the right-hand man of some noble who had purchased a cannon. And the noble asked, "What angle do I put the cannon at to get the longest range?" Very simple, direct question. But nobody really knew. And instead of going back and reading what Aristotle might have said about it, he drug the cannon outside of town to a field and began to shoot it, and by trial and error determined that around 45 degrees you get the maximum range. Starting to look like science. So why are we talking about these other ancient things now? Well, our lives are dominated by science, whether you understand the science or not. I mean, the technology in this cell phone is mind-boggling. And I can connect with almost anybody on the planet who has one of these. If you call my buddy in Russia and demonstrate, but I won't. So, what this book is about is that everyone, not just scientists, but everyone needs to have a certain scientific literacy. And when people are discussing things and discussing issues, political or otherwise, most people will assume that you have a certain level of scientific knowledge, that you know what an atom is, that you know something about maybe Newton's laws of motion. But the message today is that our hobby, ham radio, provides a wonderful introduction to science. And it's based on the most important science that there is. And I'm on a very brief presentation tell you how that came to be. I've already talked about the first statement there. Marconi did not invent radio out of the thin air. Okay. He was standing on the shoulders of some real giants. Well, we're going to talk about a few of those. For thousands of years, people have known about static electricity. If you ever rubbed a cat in Minnesota, you know about static electricity. Okay. In 1600, a fellow named Gilbert studied this amber effect, and he knew Greek, which I don't know if anybody in this room does. Maybe you know, anybody know Greek? Okay. Is this true? The word for amber in Greek is electron. Hence, this effect was named electricity. I had pretty much forgotten about Gilbert until I was looking up these facts, and his name popped up several times. For 1600, he did some very impressive work. Now you skip forward 185 years, and Charles Coulomb figures out the inverse square law that describes the forces between two electric charges. Now, this is very basic. To do that, he had to build a rather clever device, a torsional balance, and he had to make sure that the objects he were charging were spheres, and there weren't a lot of geometry effects. Other people would look at the forces between plates and things, but by doing his experiments a bit more carefully, he came up with the inverse square law. And I noted down here, you might not be able to read it, Newton had published the inverse square law for gravitation almost 100 years before. People still don't know exactly how gravity works, but Newton was able to derive a law that described it very well. And 100 years later, Coulomb figured out that electricity obeyed the same inverse square law. Jump ahead another 50 years. Gauss, well, let's back up a second. This force between two charges gives you this concept of an electric field. If I take I've got a charge here that's creating something out here that's creating a force on this. Now this is really radically new idea. This is force at a distance. Before, if I want to move this chair, I've got to put my hand on it. Okay? Well, if you get down to the atomic level, I'm not really putting my hand on it. There's electrostatic forces involved in pushing it. As far as my real world experience goes, I'm just pushing on it. But now you've got this object, you know, a foot away from this thing, and you can measure the force between the two. This is like magic. So, Gauss, if you take the amount of force on this charge and divide that force by the amount of charge on this ball, you get something called the value of the electric field there. So if you have a little test charge, you move around different spaces, you measure the force at work, you can describe this field. It has a certain magnitude and direction. It's the vector field. It's the electric field. Should you use that to communicate? Well, you know, if I had a way to measure the force here, and then I double the charge here, I feel that change. Or if I move this one, and then I would feel the force change here. So theoretically you could, but since the field falls off its 1 over the square of the distance, you're not going to communicate very far. It's a very short range thing. So, no communication devices came out of that, but now you have force at a distance. Now, also going back thousands of years, people knew about this funny thing called magnetism, which happens to be named after a region in Greece where people would find these lodestones, naturally magnetized pieces of iron ore. which if you hung it from a string, it would line up with the Earth's field. So they didn't know why it would point north, but it did. Okay. It took until 1600, 2,000 years, before Gilbert, there he is again, published that the Earth is a big magnet. And this is the reason that the compass, which is magnetized like a lodestone, points north. You know, this is a fact that's in everybody's science literacy kit. You know, most people know the Earth's a big magnet, the compass is point north because of magnetism, right? You don't have to explain that to most people. Now you have to go ahead 220 years and you get to Ampere and found out the relationship between current flowing through a wire and the magnetic field. It's created by a current. It's static, it's constant current creating a static magnetic field. You'll also notice that if you really do something big in science, you get a unit named after you. Okay? There is not a unit of Marconi. Not that I don't like Marconi, it's just that he developed things, but they're not on the same scale as what it took to make these discoveries. Now, electrostatics and magnetostatics are just that. For static, you're talking about a constant current or no currents, just charges. And I guess what I want to say is that those situations, you have magnetic fields and you have electric fields that are extended out in space, and you know, think about a simple DC circuit. Okay, you got a battery, you've got a resistor, and they're connected by wires. You've got a current flowing through that, and we all know that there's a voltage. The voltage drop from the battery is dropped across the resistor, and that resistor is heating up, so you're transferring energy over here, you're doing the work, and the currents, E over R, and the power is I squared R, with Ohm's law. Now, how does that energy being transferred? Well, what does it mean if you got 10 volts up here on this wire, positive, what does that mean? What it means is the power supply sucked some electrons off that wire and left a net positive charge. And it powered them up down there on the other wire. And there's now an electric field that goes from the top wire down to the bottom wire. Okay? If you cut the wire so there's no current going through it, that's it. You've got this electric field sitting there, going out into space and decreasing as, if it's a long enough wire, it goes down as 1 over R, but for short wire, when you get far enough away, it's 1 over R squared. Okay, but there it is. You separate some charges with that battery, but no energy is being transferred, no work's being done. You connect it to the resistor, you still have 10 volts. The battery's supplying enough current to keep the voltage there. You still have the electric field, but now you've got a current. That current creates a magnetic field around that wire. And there's a quantity called a Poynting vector, which depends on the product of the electric field and the magnetic field at any one point. and it's actually the cross-vector product. But if the E field's that way, the magnetic field's this way, Poynting vector points like that. And it's pointing the way that energy is flowing. So when you have a perpendicular magnetic field and electric field at the same point, that means power's flowing. Okay? So in this simple DC circuit, these fields are there. And you can think of the energy being transferred through the field, not through the wire. If the fields were not there, the energy would not be flowing. So, these kind of concepts were known, but in about 1819, things started to change. Oersted discovered that electric current can influence a compass. Okay, that's still a static magnetic field. But in 1831, Faraday found out that a time-varying magnetic flux through a loop induced a voltage. Now this is a game changer. Okay. And a little over 30 years later, James Clerk Maxwell published his dynamic theory of electromagnetic fields. And his famous set of four equations, which has given many engineering and physics students fits.
No kidding.
Yeah. Wrapped it all up. And to say it very briefly, Maxwell's equations unified electricity, magnetism, and optics in the field of electromagnetism. He showed that radio waves, Hertzian waves, if you will, and light are the same thing. Big revelation. Big revelation. That fact led to many things. One, in 1905, Einstein's trying to understand how these laws work when you're in different frames of reference. And it caused him to come up with this theory of relativity to explain how Maxwell's equations could work in these different frames and everybody be happy. You don't get any bigger than that. Okay? And by the way, Einstein didn't get his Nobel Prize for that. He got it for the photoelectric effect or something, not for relativity. I always wondered about that one. Okay. So, Maxwell's saying, you know, electric and magnetic fields obey these laws, and there should be radio waves. Now here's, when I was talking about the static, or the DC circuit a minute ago, the point is, you don't get any radiation off of that circuit. If you have constant arrangement of charges, or you have steady currents, there's no energy flowing out away from this thing. But if you change the currents and the voltages such that those charges accelerate, that acceleration generates a little wrinkle in that electromagnetic field that propagates out. That Poynting vector goes out. And it's that transverse component in the electromagnetic field that's due to the acceleration of charges in the circuit that causes the radiation. And Maxwell knew this in great detail in 1865. But I don't call him the father of radio, because he didn't make a radio. Here's the man that made a radio, Hertz, who has a unit. He has a unit. He made a radio. He didn't get it outside the lab, really, from what I understand. And, but he made receivers, he made transmitters, and he very carefully ruled out any other effect besides electromagnetic radiation. Now, so here it is. What happens after this? 1860s, in the mid-1880s he published. Okay. By about 1895, you have Tesla, who's moved from Serbia to New York City, but it heads with Edison. He's gone to work for Westinghouse, and he goes off on his own. And he starts making remote controlled submarines and other gadgets, mainly to get money, I think, to impress people. But I really can't tell you the details about those, but I think they were pretty much resonant loops that weren't quite radio. Then Marconi took these ideas and in his experiments, first transmitting over distances of a mile or two, and then very quickly increasing until he did the transatlantic experiments just a few years later. And most people do view Marconi as the father of radio, because he really got outside the lab and made it into a world-changing device. And then the man I would call the son of the father of radio is Armstrong. As far as I'm concerned, he's the man. 1913, the regenerative radio receiver. And if you read his book, which I read several years back, if I remember correctly, he's fiddling around in this attic room where he built his radios and things when he was still young. And he came across trying this idea of the regenerative feedback. And other people were hearing stations maybe 50 miles away. And that night he was hearing stations thousands of miles away. And he was the only one doing it. This is a regenerative receiver from about 1923. It says National Supply on it. It's actually Crosby, I think. It's called an Ace Type 5. It has one tube, and you're going to get a kick out of the variable inductor and the variable capacitor in here. So this is the pass around. And be sure and open it up and take a look inside. If you've got a 90-volt battery and a couple other batteries, you can turn it on. Now if you read the label, it refers to Armstrong's 1913 patent for the regenerative receiver. Armstrong went into the Army in World War I and helped use radio on airplanes and various things, even in World War I. Comes home, and in 1919, he's now at Columbia University. He's already been there, and he happens to produce the Superhit receiver, patented in 1919, I believe. And then it took him a whole another 14 years in 1933 to patent FM radio. Well, that's a slam dunk. I mean, there's just nobody that compares. So in terms of modern history of radio, it's Armstrong. But in terms of the deep magic, in terms of the pre-1900 radio, it's Heinrich Rudolf Hertz. Now I'm going to finish this just by repeating that ham radio stands on these ideas. And if you can use ham radio to capture some kid's imagination or some older kid's imagination, and then give them access to materials that really understand the science behind the radio, you'll do that person a big favor, and I think the world will be better for him. So thank you.
Any questions for Tom?
You know where DeForest fit in? I know he made the tube. Did he do anything with it?
Well, you know, DeForest wasn't Armstrong's favorite fellow.
No kidding.
I guess I really don't know. I haven't really dug into the history of that, but from what I have read, I don't know that it's really demonstrated that DeForest truly understood what was happening. And there's no denying that Armstrong understood very well what these circuits were doing. You look at the picture of that first FM transmitter receiver, it's almost as big as this table. I mean, it's a very complicated thing. So I guess I'll just leave it at that. I don't know that much about the force.
In the 1950s, Armstrong wrote an autobiography, I believe, called The Father of Radio. He had a more extensive idea of what his contributions to radio were than apparently most other people have. There was,
Yeah, I'm gonna come down here because I didn't get that last point.
I believe Armstrong wrote an autobiography in the 1950s called The Father of Radio, which suggests that he had a more aggrandized view of his role in radio than most people have.
Armstrong write it or somebody else write it?
I think he wrote it.
Well, then that's certainly probably biased, but, and it is, of course, tragic how he ended up. But I think his actions demonstrated that he had a very powerful understanding of radio. I mean, it was, I don't know, didn't tend to be biased or not. I mean, what did DeForest?
So DeForest wrote a book where he apparently viewed himself as being the father of radio, apparently.
DeForest or on DeForest?
DeForest did.
Oh, that's what I mean, I didn't understand. That's,
Yeah.
I guess that's the whole point, isn't it?
Yeah.
I think on the patent, when he was trying to get his patent, as I understand it, he was trying to explain some of these concepts, some very simple ones, and he got completely flustered and couldn't do it. And so that's when they kind of said, well, you don't understand it, and they took some of it away. So there's back and forth between them. That's why the
There was a very good
Nobel.
documentary
Yes.
that I've seen that compared the two's back and forth.
In fact, I've got it. I've got the video.
Yeah.
We could play that sometime. It was
Yeah.
very, talking about this history back and forth between them.
And how Armstrong created some stuff like the FM radio, and he had it in a certain band. And then DeForest, I think, or someone
I
with
think it's
RCA.
David Sarnoff.
Sarnoff, that's what it was.
It's a different conflict.
I know,
Okay.
but someone else came into play there and said, well, we're gonna put FM radio up here at that band, at that frequency with, you know, politically did that. And it just wiped out Armstrong's,
Yeah.
production of FM radios.
Yeah, Armstrong's story deserves its own hour.
Yeah.
Definitely. But today I wanted to not even get to 1900.
Like, one thing Armstrong did, I guess, was he was the first bona fide developer of a commercial mobile rig for police departments. So all of us with our mobile rigs can probably look right at Armstrong as the original resource there. He was commissioned, I guess, to build a base station, and apparently what police would do, they'd call in and they had receivers. They call in on a phone, and then it would get aired out by the dispatcher over a base station transmitter, so they'd all hear it on the receivers. But to get back to the base, they'd have to stop and use a phone somewhere. And Armstrong came along with a mobile FM transceiver, or transmitter at least, to close that loop. Or I think it was like maybe Phoenix or some southern city. So we can at least thank him for that.
Yeah, I wish he had had that impact on aircraft radios. I think they're still FM, I mean AM.
Yeah.
He didn't get there quick enough. Okay, any more? No.
All right, thanks, guys.
Sure.
Got this down.